algebras in this second context in terms of primitive ideals, and then to give applications and motivations, particularly to the rationality of W algebras. But from now, I can explain a little bit what I want to do, because here, the typical varieties that we will encounter are the following. So Q here is an integer. For the moment, just assume it's an integer. And then I denote by NQ the variety of X in G, where G is as before simple algebra, such that the image of the adjoint action power to Q is equal to 0. Okay, and by definition, this is clearly contained in the nilpotent cone of G. And much less trivial is that NQ is actually irreducible. So this is not clear at all from the definition, but it is true. And as a consequence, NQ is just a closure of some nilpotent orbit that I like to denote by OQ. So OQ is a nilpotent orbit. Okay, so this is a typical varieties we will see in this context. And as I mentioned, our result is to express this in terms of primitive ideals. So this is the main result I want to discuss and explain why it can be interesting. So as you see, this a priori has nothing to do with vertex algebras, because you can describe NQ without referring to any vertex algebras. But our proof uses a representation theory of admissible affine vertex algebras. And moreover, our motivations come from this context. All right, and the last context I want to discuss, in fact, we later discover that we can also express these varieties in terms of the small quantum groups. So and we discover this thanks to remarks of Anna Laszowska. So I would like to thank her again for this comment. So here, this appears in slightly different way in Tomoyuki's talk. So I will give more detail later, but zeta here is a primitive Q roots of unity with some condition of Q, but it's not important for the moment. And so here we can connect NQ with the small quantum group. So here again, I will detail this later, but the connection between NQ and the small quantum group suggests that there is a strong connection between the representation theory of admissible affine vertex algebras and representation theory of the small quantum group. And this is precisely what Tomoyuki explained in the previous talk. And he is currently studying this with Thomas Krutschis and Kawazetsu. So suggest a strong connection between representation theory of, let's say, VKG. So here, this is affine. So maybe I write by words, admissible vertex algebra, and of the small quantum groups. Okay, so this I will explain at the end of my talk, just the connection. So the plan of my talk is roughly this. I comment these three contexts and relate each other's. Okay, so let me recall some standard facts on primitive ideals. So G is as before simple, and then if I have a two-sided ideal in the enveloping algebra, then the corresponding graded ideal for the PBW filtration gives an ideal in the symmetric algebra by the PBW theorem, which is canonically isomorphic to the coordinate ring of G star. And what we call the associated variety of I is the zero locus of this ideal. So it's a set of X in the duals of that Fx is 0 for all F in I. All right. And when I is a primitive ideal, so I recall that this means that I is the annihilator of some simple left UG module. Then we have two important results that I want to remind you. So the first result is due to Duflo and says that in fact I is the annihilator of some irreducible highest weight representation. So it says that if I is primitive, then there exists lambda in the dual of Cartan. So here I have a triangular decomposition such that I is annihilator of the corresponding highest rate, irreducible highest rate representation. And the second result, which is due to independently Joseph and Kashiwara Tanizaki, says that actually if I is primitive, the associated variety is first of all contained in the nilpotent cone. This is not so hard to see. And the hardest part of the theorem that says that in fact the associated variety is irreducible. So altogether, this means that the associated variety is the closure of some nilpotent orbit. All right, so now it's natural to wonder, combining these two results, it's natural to wonder what are the connection between such a lambda and the nilpotent orbit O. And when O is a special nilpotent orbit, we have a precise connection. So when, maybe I give this definition for special, when lambda is integral, then O is such O is called special. So this coincides with the notion of special nilpotent orbit of Lustig. And in this case, we can describe more precisely the connection between lambda and O. So more precisely, we have the following result due to Barbash and Vaughan that I want to remind because we will have some analogous result later. So the theorem says the following. Yeah, maybe first I remind that we have order reversing a bijection between special nilpotent orbit in G and special nilpotent orbit in the Langlands dual. So special nilpotent orbits in G and special nilpotent orbit in the Langlands dual of G. So maybe I like to denote by OCH the corresponding nilpotent orbit. So I can pick here an SL2 triple attached to this nilpotent orbit. So here E belongs to O. And then I denote by HH, HH, a corresponding SL2 triple here. And then I can assume that HH belongs to the Cartan subalgebra of the dual of GH. So this means which canonically identify with the dual of H. And also I can assume that this element is dominant. And then I denote by lambda O the half of this number, of this linear form. All right, and then the statement of Barbach-Vaughan and roughly that lambda O correspond to the lambda in the theorem. So the statement says that if O is special, then the associated variety of, maybe I would like to give a notation for annihilator for the sequel. Yeah, I denote by that. So here, this will be lambda O minus rho, where rho is as usual the half sum of positive roots. And this is exactly the closure of our special nilpotent orbit. And moreover, this lambda, it's not unique, of course, satisfying this, but is minimal in some sense. Lambda O is minimal in some sense. So in particular, it means that it implies that if mu is a weight such that the variety is the same, we have this, which is the closure of O. So that is, it is the closure of this one. Then either mu is lambda O or the norm of mu is strictly bigger than lambda O. So it's minimal in this sense. All right, so we will see that we have analog results in the context of affine vertex algebra, so that's why I want to mention this. But in our context, the nilpotent orbit, so Q that will appear, that I mentioned in the introduction, is not special in general. So in what I will do later, I will need to consider non-integral weight. Also, this is motivated by this analogous result. All right, so I guess there is no question about this classical part. So I would like to go now to the setting of affine vertex algebra. So in particular to Katsuwakimoto algebra. All right. Okay. All right. So now I would like to consider affine vertex algebra and corresponding associated variety. All right, so here I consider the corresponding Katsuwakimoto algebra. All right, and then I consider the universal affine vertex algebras at level k. So for the moment, k is any complex number. And I consider the following induced modules that we already encountered in the previous talk. So here, CK is, as usual, one-dimensional representation of the subalgebra here. And here, CT acts trivially, and K acts as K identity. So this is a universal affine vertex algebras. And I remind you that a VKG module is the same as a smooth G-hat representation of level K. Okay, so here in this setting, there is no a priori satisfying notion of associated variety attached to the enveloping algebra of G-Chech. And so we get a better analog by considering associated varieties of VKG, which through this correspondence plays also the analog role of the enveloping algebra. So the construction looks different, but the point is to construct associated variety which plays the same role. So the general idea is the following. To any, but not completely general, I stay in the setting of affine vertex algebra for the moment. So to any graded quotient of VKG, the idea is to attach, we attach a Poisson variety so maybe let's denote by V this quotient, and this Poisson variety will be denoted by XV, which captures some information about V. So in particular, maybe I recall that VKG is not simple in general. And if we denote, as in the Tomoyukin-Stokes, the unique graded simple quotient, we will be particularly interested in the associated variety of this simple quotient. So let me explain the construction, but first, through the previous correspondence, this is the highest rate representation of irreducible highest rate representation of G hat. And so this variety should play the role of associated variety of primitive ideals. So let me explain the description of this XV for any graded quotient of VKG. So the construction works as follows. Okay, so V is any quotient of VKG. And to understand the construction, maybe observe that by the PBW theorem, VKG is isomorphic as vector space as the enveloping algebra of T-1 G, T-1. And now I would like to consider the following quotient of V. I quotient by this part. Okay, so I kill all elements with a power in T power -2 or greater than T-2. So this is what we call in general the zoo C2 algebra of V. And this is naturally underread with a Poisson structure. So maybe I just make a remark that in general, if V is any vertex algebra, RV is defined to be V divided by what I like to denote like this, where this is the span of element of this form. Sorry. And I'm just saying that this space is nothing to do but this one. So, and here the Poisson structure in general is given by, if I denote by bar the image in the quotient, this is just A0B, where AN is the Fourier mode of the vertex algebra, and the product just come from the normally ordered product. Okay, so for those who know vertex algebras like this, this is a general construction, and if you don't know so much, I can explain in the setting of affine vertex algebra the Poisson structure because it's easier. In this setting, we have the following map, starting from the symmetric algebra. So here I send an element in G to an element in this quotient as follows. I just take xt-1 with the vacuum. So here the vacuum is just the image of 1. So I take the image in the quotient V, and then it's modular the T-2 G T-1 V. Okay, so this is the construction. And this map, it's very easy to see that this is an isomorphism if V is a universal one, vertex algebra. So that RVKG is just isomorphic to the symmetric algebra. And that I didn't say, but what is the associated variety? By definition, is a reduced scheme associated with RV. So it's a spectrum of RV, and I take the reduced one. So here in particular, it says that X of VKG is just a dual of G that I identify with G using the killing form, for instance. All right, and in general, if V is any quotient, then we obtain, here we have a surjection in general, and you can transport the Poisson structure comes from here, the Poisson structure of the symmetric algebra. And in general, for any quotient, so this is a G invariant closed cone of G star. All right, and okay, so this is just what I want to say. And so in particular, it works if V is a simple quotient. But in general, it's difficult to compute these varieties. But we have families where we can compute it. So maybe one remarks that contrary to what's happened for primitive ideals, this variety, even for the simple quotient, no need to be contained in the nilpotent cone. But we have the remark is clear because sometimes VKG is simple already. So of course, in this situation, the simple quotient, the associated variety of the simple quotient no need to be contained in the nilpotent cone. And with Chuipo and Arakawa, Chuipo-Yang and Tomoyuki Arakawa, we have a more precise statement about this, which says the following, that this one is simple if and only if the associated variety of the simple quotient is the wholly algebra. So the direct implication is clear, but what is less trivial is the other direction. And so this gives a geometrical characterization of the simplicity. So in particular, you see that if Q, for instance, is not rational, this variety is not contained in the nilpotent cone. All right, so now let's concentrate on family where this variety behaves like primitive ideals. So this is, now I would like to consider admissible level. Okay, so here I would like to give a definition of admissible weights, which is due to Katsuwakimoto. So, okay, I consider any weight for the moment, and we say that this weight or equivalently the corresponding highest weight representation of G hat. So this is my notation for highest weight representation of G hat. Is called admissible if we have the following conditions satisfied. So the first condition is that lambda is dominant and regular. So we have something like that. Okay, so this is the integral lattice of lambda. So this condition, okay, maybe I comment after. And then the second condition says that the rational, the vector Q vector space of this lattice is coincide with the Q vector space generated by this lattice. All right, so this condition looks a bit technical, but they are designed so that the character of the representation L lambda is a modular function. Actually, the first condition ensures that it is a modular form, and the second ensures says that it is actually a modular function. And in fact, Kat and Wakimoto classified all such weights so that they came to this definition. And conjecturally, they expect that admissible weights correspond exactly to those who satisfy this condition. Okay, so what about the weight K? So maybe just for our purpose, what I want to say is that this weight is admissible. So I will say for sure that K is an admissible level if we have the following very easy description. K plus dual Coxeter number is a rational numbers, so with PQ coprime. Sorry. Such that P is greater than the dual Coxeter number if Q is coprime with the lacity of G, and P is bigger than the Coxeter number if Q is not coprime with the lacity of, is equal in fact to the lacity of G. So here our charge is the lacity, so this means is 1 for type ADE, is 2 for type BCF4, and this 3 for type G2. All right, and in particular, if K is a positive integer, so this means that LKG is integrable representation, then K is admissible. So it is what Tomoyuki mentioned in the previous talk, admissible representation contained, but it's strictly much, much bigger than integrable representation. All right. So if K is admissible, now we have a result of Arakawa that will be important in this talk, and conjecture by Fegin-Frenkel that if K is admissible, then maybe I want to describe like this, the associated variety of LKG. So here I remind that K is written like this. So Q is the denominator of this number, is the variety NQ that we encounter in the introduction if Q is coprime with the lacity. And we have a closed variety that I haven't discussed before, but just technical things that I denote by L for Lagrange dual, if this is equal to RHH. So NQ I already described, so maybe I remind you. So this is a set of X in G such that A at X to Q is equal to 0. You can rewrite as the corresponding highest rate representation is the highest positive roots. So if you write like this, and then the other one is the X in G such that P. So here you consider the highest short root of X to Q. Here I divide by HH is equal to 0. So this corresponds to the highest positive short roots. Okay. And okay, so this is a result, and in particular, it's contained in the Nilpotent cone, and Tomoyuki already explained why this is already interesting. But moreover, because it is irreducible, these two varieties are irreducible, this is actually the closure of some Nilpotent orbits. So it was denoted by OK previously, but in fact, it depends only on the denominator. So I prefer to denote it OQ. All right, so this is the very nice statement, because in particular, it means that the variety here is irreducible in this context. Okay, so I would like to notice that we have this irreducibility property, which is not clear at all in the context of affine vertex algebra and more generally, but we have a conjecture with Tomoyuki, which says the following, that we conjecture that if this variety for arbitrary K, not admissible, of course, is contained in the Nilpotent cone, then LKG is actually irreducible. And in fact, we have, they exist K not admissible, such that this variety is contained in the Nilpotent cone. And in all examples we obtain, of course, this is satisfied, but we haven't any proof. And here I notice that this condition exactly means that the variety has finitely many symplectic leaves. So we have, in fact, a more general conjecture. So more generally, if V is any, let's say, simple vertex algebra such that XV has finitely many symplectic leaves, then the variety is irreducible. All right.
Is it also conjectural equivalence?
Sorry?
Is this equivalence also conjectural?
Oh, no, this equivalence, it's clear. It's clear. This one is okay. This is clear because, in fact, the associated variety is in G invariant and closed. So as soon as you have a non-nilpotent element, you contain the closed G invariant cone generated by semi-simple element, and this has infinitely many symplectic leaves. So this observation is clear in this context, that saying that it has finitely many symplectic leaves is equivalent to be in the nilpotent cone. Is it okay?
Absolutely.
And as I said, I say that there are examples where K is not admissible and this is contained in the nilpotent cone, but there is also example where K is such that VKG is not simple, but we don't have this condition. It's, for instance, a sheet closure, and in this case, it's not. There is no finitely many symplectic leaves, so everything can happen. But so far, every example are irreducible. But we conjecture only in this setting. All right, so this is a slight digression. So now I would like to state our main result. So as I mentioned, I want to express NQ, but also Lagrange of NQ in terms of primitive ideals, and then give application and idea of the proof. So main result. So the statement is, is very easy to state. It says that, so let's assume that K is admissible as before. And then if Q is coprime with the lassity, then the variety associated with lambda rho, it's rho over Q minus rho is the closure of this nilpotent orbit. So here, this is not integral weight. Huh? As I already mentioned, no Q, no need to be special. For instance, in G2, all nilpotent orbits are pairs like this, but it is known that the minimal and A1 tilde are not special. And if Q is not coprime, then what we have here is that we take rho change. So this is the half sum of co-roots minus rho is the closure. Sorry, here I should, okay, what I wrote is correct, but maybe I prefer to write like this. Okay, and this is indeed this one. Okay, so the proof breaks into two steps. So first of all, we use representation theory of vertex algebras to show one inclusion. So this I will quickly mention. So maybe for simplicity, I like to denote by lambda q the weight that appears here. Is contained here. And then we have a combinatorial formula due to Katz, Elashvili, and Winberg. It's not so old, it's maybe 2009, which says that, in fact, we can check the dimensions. So which says that thanks to that, we have that these two irreducible varieties have the same dimension. So of course, on the right-hand side, it's easy to compute because we have explicit expression of OQ, and the combinatorial formula of Katz, Elashvili, Winberg allows us to compute the left-hand side. So I don't comment the second part. It's not so beautiful because it's case by case, but I would like to discuss the first part. And also you notice that also the statement no does not refer to vertex algebras. The proof used vertex algebra. Okay, so let me comment a little bit the idea of the proof, the first part of the proof. But yeah, I comment that and then mention applications after. So idea of the proof for the first part. Huh? All right, so first of all, we have the following result proved by Arakawa, which use strongly the concept of associated variety. And this illustrates how powerful is this tool. So it's a result of Arakawa, and it was a conjecture of Adamovich and Milas, who proved the conjecture for SL2 hat. So the statement is the following. I consider an admissible weight that I like of level K that I like to write like this. So this is admissible level. Admissible weight of level K. And then the statement says the following, that it says that L lambda, so the highest weight representation associated with the lambda, is LKG modules if and only if the integral root associated with lambda is isomorphic to Z1 associated to K lambda 0. And this one is easy to describe. So this is a condition. Okay, so no need to express this combinatorial condition, but what is important is we have a characterization of lambda to be such that L lambda is a LKG module. And now the key point in our proof is that our lambda Q, so lambda Q hat associated with our lambda Q, as in the theorem, satisfies this condition. So maybe I call it star, plus it is admissible. So this is a key point. And now what is the link with associated varieties? The link is the following. By those correspondence, we have that we have the following, that we have that, sorry, here I forgot hat. This is the weight associated with lambda hat, not lambda, sorry. So we have that this condition appearing in the Arakawa's theorem is satisfied. This implies that the corresponding highest weight of G, corresponding to the restriction of lambda hat to the carton, is Zoo by the module over the Zoo's algebra of LKG. So in general, the Zoo's algebra of a vertex algebra is a certain non-commutative algebras, and the Zoo's algebras of maybe I mentioned that the Zoo's algebra of the universal affine variety is universal affine vertex algebra is just the enveloping algebra. And so here, this is a certain quotient of the enveloping algebra. let's say jk. Okay. Okay, so at the end, we have that for lambda q, we have this, which implies that in the setting of G, we have this statement. And this implies, so now this is easy, this implies that the annihilator of LG lambda, that I denote as usual by G lambda, contain this ideal JK. And so now we go to associated variety. It implies that the associated variety of JK is contained in the, sorry, it's a converse. It says that the associated variety of J lambda is contained in the associated variety of JK. And now there is a general fact. So this you can write as the corresponding scheme of the graded algebra of the Zoos algebra of LKG. So in general of V. Okay, maybe I take reduced scheme. And this is a general fact that this is contained in the associated variety. So anyway, here what we get in this setting is that it is contained in the associated variety of LKG, which is nothing to do but our closure OQ. So at the end, we have this expected inclusion. And in fact, in the admissible case, this is just a remark, but here we have equality because K is admissible. This is also proved by Arakawa. So this explains inclusion. So as you see, it's really used the representation theory of vertex algebras. And I already mentioned that the exact equality comes from a combinatorial formula for dimension. But now our theorem says the following, is that for lambda q, we have the precise equality. So the theorem says that for lambda q, we have a candidate which makes the equality. And moreover, we have also a minimality like in Barbach-Vaughan theorem. So moreover, in this story, L lambda q hat has the minimal conformal dimension. So the conformal dimension is a higher minimal eigenvalue for the coming from the Virasoro action. Maybe I explain this. So this is minimal L0 eigenvalue coming from the Virasoro action. So some Virasoro act on LK. All right, so this has this minimal conformal dimension among simple LKG modules in the category O. And in fact, so the minimality can be expressed as follows. So from any mu hat admissible with a property star, as in Arakawa's theorem, the variety of G mu is contained in the variety of G lambda q, which is exactly OQ bar by our theorem. And with equality, if and only if mu is either lambda q or, so here we have less strong statements than in Barbach-Vaughan, but we have that G mu is equal to G lambda q. So this is the analog of Barbach-Vaughan, But now I would like to go to the Brst reduction. So that is to say to the setting of W algebras, where the minimality condition will be, first of all, stronger and also more interesting for some reason I want to explain. Sorry, I'm a bit late, so maybe I go faster. Okay, any question about this main result and first comments? No? Okay, so now I would like to give some motivation and application to W algebras. So this is my rationality of W algebras. So here I pick F to be a nilpotent element, and I denote by WKGF the corresponding W algebras, which is obtained by the Drinfeld-Sokolov reduction applied to the universal affine vertex algebra. So this is to say it is obtained by Brst reduction. Okay, and this is W algebras of level K. And this is well known to have a vertex algebras structure coming from this Brst reduction. And moreover, by a result of Katz and Desolé, we know that the associated variety of the universal W algebra is a Slodový slice associated with an SL2 triple containing F. So this is F plus the centralizer of GE, where this is an SL2 triple. And the Poisson structure of this Slodový slice is obtained by Hamiltonian reduction from the Poisson structure of G or G star. And what is very nice is that this Brst reduction is compatible with associated variety, in the sense that for all quotient, graded quotient V of VKG, we have that the associated variety here is just the intersection with Slodový, like this. So this is a very pleasant construction. And in particular, you see that this, this variety is just a point. So in particular, it's just F, if the orbit of F is contained in the associated variety of V. So this condition is known to be, refers to as Lee's condition. This means that this vertex algebra is Lee's. In general, for V a vertex algebra, V is called Lee's if the dimension of the associated variety is 0. So in this setting, it is easy to check whether this W algebras is Lee's. All right, and close to the Lee's condition, there is a rationality condition. The rationality condition says that vertex algebras is called rational, is any graded module is completely reducible. And we have a famous conjecture of Zhu, which says that rationality implies a Lee's condition. And both are known, these two conditions are known to be very interesting because Lee's or a rational vertex algebras has very nice properties. So the converse is known to be not true. So this is only in this direction. And for W algebras, we have the following conjecture of Yeah.
Question. Can you just repeat this conjecture because I can't read what's written?
Sorry. So the conjecture is general conjecture that if a vertex algebra is rational, then it is automatically Lee's. And Lee's, it's a geometrical condition which says that, okay, maybe I'll write better. If V, the condition, if V is rational, so any V module is completely reducible, then the associated variety has dimension 0. This is a conjecture. Is it okay?
Yes, thank you.
Yeah. Okay, so this is still open, but in the context of W algebras, we have another conjecture of Katsuwakimoto, which has been now recently proved in full generality by McRae. So McRae, I should write better the name, McRae, in 2021. So it was for a long time a Katsuwakimoto conjecture and proved in particular cases, but big family by several people. So yeah, I want to mention, sorry? It's okay. Pascal, etc.
I think something is unmuted, right?
Ah, sorry. What I did?
Yeah, no, not you on, but right, we had an echo.
Yeah, I know.
I think now it's fine.
Okay, sorry. I lose the full screen, but maybe it's okay. Okay. So Krustich, Linshaw, etc. in particular. Anyway, so the conjecture says the following, is that, okay, K is admissible as usual. And then I did not I pick F in OQ so that the simple quotient of the W algebra, so this is a simple quotient of W, the universal one, which is a quotient of the Drinfeld-Sokolov reduction of the simple one, and conjecturally the same. But anyway, we don't need it is equal, but anyway, if we have F exactly in OQ, this one is Lis. Because the associated variety of this one is precisely the orbit closure of F. All right, and so if it is Lis, then it is also rational. So it's a kind of evidence on this conjecture in this setting. So as I said, this is now proved. And what is the connection with our result? And I'm sorry, yeah, I have to be a bit quick. So the connection with our result is the following. So if K is admissible as before and F is, so K admissible and F in OQ as in the previous theorem, then there exists a simple, unique, simple WKGF module with minimal conformal dimension. And this conformal dimension is precisely, I denoted by H lambda Q, but it is precisely Z1 corresponding to how to say, module of LKG of the simple one corresponding to the Drinfeld-Sokolov reduction applied to the Zoo's algebra in some sense associated to this ideal G lambda Q. Okay, so this is a bit technical, but just what I want to mention is that there is a unique WKGF module with minimal conformal dimension, and this minimal conformal dimension is precisely obtained from this lambda Q, which makes the minimal dimension for the simple affine one. So this is a connection. And why this is interesting? It's because, in fact, we conjecture a more general fact. We conjecture that if V is conformal, Lis And okay, plus some technical condition. Well, maybe I write the condition. It's self-dual, but it's not so important. Then there exists a unique simple V module with conformal dimension, with minimal conformal dimension. And this is useful to prove that the category of V module is a modular tensor category. So this is, if this conjecture is true, this is nice. And our results say that this conjecture is true in the setting of W algebras. So, okay, to finish, I would like to say just one word about small quantum group because the connection is very easy to state. So I just need 1 minute, if you don't mind. Okay. Maybe I just finish with this, with the connection. So it's the last part, but very short. So what is a connection? So here I assume that Q is odd and not bad prime for G. So this is just a technical condition, but for instance, it implies that 3 should not divide Q if G has type G2. And then I pick zeta to be a primitive Q roots of unity. All right, and I denote by U zeta of G the small quantum group corresponding to zeta. And the statement is the following. The cohomology algebra of U zeta has been described for Q big enough. In fact, we have the result of Ginzburg and Kumar in 1993, which says that if Q is greater than the Coxeter number, the cohomology algebra of this small quantum group is just, maybe I write like this. Yeah, okay, I did not like this. It's a coordinate ring of the nilpotent cone. And more precisely, it's concentrated in odd, even degrees. So this is 0, and so this is 2 odd part. And more recently, there is a result of Bendal. So Bendal, Nakano, Parshall, and Pilen. So this is more recent. I forgot the year. Maybe, yeah, 2014, which give an answer for smaller q. So in fact, for any q as before, odd and not prime. Sorry, for Kumar and Ginzburg, there is no restriction, of course. So it says that, in fact, we have similar setting, and which appears here. It's precisely our NQ. So maybe I write like this to avoid, to distinguish case. So we have this result, and it's also 0 for odd part. So, and then of course, we recover the previous one for Q big enough. So here it's a connection, but unfortunately, our proof is just a case by case. In fact, here in the results that don't express like this, it turns out that with this condition on Q, this nilpotent orbit is actually a Richardson nilpotent orbit, and they have a description like this, where this is a nilpotent radical of some parabolic, and this parabolic only depends on Q. And so we can check case by case that their description correspond to our description on OQ. But it will be very nice to have a more conceptual proof of this statement, because as I say, this suggests a strong connection between vertex algebras, admissible affine vertex algebras, and the small quantum group. And this was illustrated by Arakawa, that we have this deep connection. So for the moment, it's just a checking, and it's really nice observation, but we don't have conceptual proof that why this is true. Sorry for the delay, I should stop now.
Thanks a lot. Any questions or comments, either here in Le Diable or online?
So may I ask a question?
Yeah.
So do you have an example on non-rational but least vertex algebra?
Yes. I don't remember if we have really proved, but I think with Tomoyuki we have an example in the line exceptional series where the K is not admissible. We have the associated variety, which is a minimal nilpotent orbit, and with some shift, we expect that if we go to the W algebra setting, we have example of least simple W algebras which are not rational. Okay, to summarize, I think we have example. The example I gave, I'm not sure if we
So
have.
the typical one is triplet algebra.
So, okay, this one is just the one you suggest is proved, is really proved.
Yeah.
Okay, so maybe this is better examples.
Thank you.
Any more questions or comments, either on site or online?
I have a slightly vague question. So, so the category of representation of a small quantum group can be interpreted somehow geometrically, something like D modules on the semi-infinite flag variety, whatever you mean by that. So, is there somehow a chance to sort of explain this relation that you were talking about in the end in this way, by using some kind of geometric interpretation of this category?
This is a very nice question. I don't know for the moment. I should mention that exploring this conceptual proof is a joint project with Tomoyuki and Anna Lashoska. So I don't know, Anna, do you have any idea?
Or maybe a related question. So sorry, can I ask a related question?
Yeah.
So in that, interpret this categories in terms of representations of the affine the algebra on critical level. Where this functor of cohomology this corresponds to some kind of semi-infinite cohomology.
Just the critical level is not in our story. This OQ does not appear at admissible level. So, of course, the nilpotent cone appears, but admissible level does not include the critical level. So
no, I understand, but I'm saying that the whole category of representations of the small quantum group can be interpreted in terms of representations at critical level.
Okay, I see. Yeah, I don't know for the moment. Yeah.
We also want to connect with what you talked in your talk. So can you connect what you did with at some critical level?
You are talking to.
I mean, I think my question also can be asked about, about Arakawa's talk that somehow there was also some interpretation in the category representation of quantum group, which using this kind of admissible levels, but there's also an interpretation using critical level. The question is if there is any kind of direct relation between these things.
So we think this should be understood in terms of the interpretation of this symplectic duality proposed by Gayotto, Krutich, and who by these people, but so it's very topic of your talk, and but so the question is, do you see somehow critical level in your construction?
No, I don't see it definitely, but somehow my question is whether you see it.
No, we don't see it for the moment.
Okay, more questions or comments? Yeah.
Yeah, I also have a question for Anhai. It's Gabriele. How far, it's like a naive question. So how close are all these statements about associating varieties to the vertex algebras? to a deformation quantization statement about the orbit. First, okay, that's it. Then I have another question later.
This I don't know. I'm not sure I understand the question. You talk about general construction?
Yeah,
So,
right. So, yes.
So we have a statement with answer if vertex algebra is quasi-Lie, which means associative variety has finite remaining simply leaves, then vertex algebra is a quantization of jets of associative variety.
But
But
this is different,
but
no?
this is not a scheme.
Yeah.
It's not strict quantization.
Okay. And okay, so there's some, okay. And what about semi-simple orbits? They are unique.
This is as I mentioned after the question, I forgot who, but it may also happen that some Jordan class closure appears in this context. But this is a bit more mysterious. And of course, this appears at outside admissible level. But semi-simple elements can also appear in the associated varieties, and this is quite different than primitive ideals context.
Okay. And one last, and then I'll stop. Do you have some statement related instead, relating this to orbits for not just G, the simple algebra, but this deeper version, this algebras of truncated holomorphic currents. So like you go G of Z polynomials and you truncate by those of high enough degree, and then like a joint or rather co-adjoint orbits for that. So I don't know if you see this appearing somewhere in your story. It's related to like G tensor jet schemes. I mean, you have this stuff in your notes on W algebras, so I thought because maybe you're quantizing those, I had the impression, but I don't know.
We can consider associated variety directly from V. It is how jet appears. You take the graded algebra of V and you consider the spectrum, and this is related to the jet of this variety. So in this way, you get some polynomial ring if you want at coordinate ring, but truncated, I don't know.
Okay.
We try to do that, but
Okay, yeah, thank you very much.
Thank you. Any other comments, questions?
And another stupid question, in your definition of the orbits OQ, they were given by the requirement that some even power of an element in the joint representation was 0. And if you take odd power, then the corresponding orbit will be eventually reducible. I mean, it will not be an orbit, but union of a few orbits, or what?
This I don't know. Actually,
No, it can be reducible. Yeah, sometimes it can be.
It
so
can be reducible.
It can be reducible. It is what you say?
Yeah.
Yeah, I think so, because this 2Q condition, even for classical case, all right, because this 2Q condition exactly means that it's rectangular, but if it is odd, I guess you can have several which fit.
Okay. I see. Thank you.
Okay. If there are no other questions or comments, let's thank Anne again.
Okay, goodbye.